Twitch? Got logged in? Upcoming. Oh, well, that's nice. Ah, so sorry for that. Why am I not allowed to do the thing? There we go. Alright, that works. Okay, so I am going to wait a bit to allow anybody who isn't here to follow through. We're going to be continuing on with bringing paths into scope with the use keyword. I like getting used, it's quite fun. Use crate front of house hosting. I do wish I could use snake case or something like that. You know what, I'm going to fork the language, rebuild the entire thing just to have camel case. I can't stand this stuff, man. One moment. I'm going to take a sip of tea. I guess I should probably make small talk, I guess, to the two people watching. Thank you for being here, by the way. I think one of them might be me. I still don't know how Twitch works. Got new hedgehogs, my father does. He's a breeder. Got like 7 of them right now. Tiny little fellas. Not so tiny anymore. About the size of a fist. Think snake case is easier to read? I agree, it's absolutely easier to read. But I am biased from years of riding in camel case. I mean, this is better. I don't care, I don't want better, I want familiar. I'm afraid of the new thing. Brings me fear. Terror even. Alright. Now they are adorable, seriously. If you're alright with it, I'll send some into the signal group. The other guys won't know what hit them. They are so cute, but they are massive. The mother does not care though. You can just kind of pick them up. Usually they're not very happy with you in there. She just could not care less. I'm trying out the tiling for KDE Plasma. Send headshot. You know what? I'll do it right now. You guys can't stop me. I don't know. You've seen my start menu. Anyone watching this, feel free to send me a request if you want to be in the Signal group. We're currently building a to-do app. Quite fun, actually. Haven't gotten too much in the way of coding so far. Work's been weird, but, you know, things will change. Looks like we've hit a third person. We're just waiting here for a moment. And meanwhile, I'm going to send hog pics. Okay, I think that's fine. Sorry for the delay. There's 4 people in here. Wow. This is the most we've gotten since the original piece. Once that timer hits... Oh, wow, they're leaving. 2 of them just left. Gone. Instantly, they heard hog and they're like, no. No, we're done. Fair enough, honestly. Just popped in, I guess. I believe I sent that. Anyway, I guess we're going to be starting. Great to see you again, Sorbet. We are going to be beginning again with bringing paths into scope with the use keyword. Having to write out the paths to call functions can feel inconvenient and repetitive. Listing 7.7. Whether we choose the absolute or relative path, the add to waitlist function, every time we want. In listing 7-7, whether we choose the absolute or relative path to add to waitlist function, every time we wanted to call add to waitlist, we had to specify front of house and hosting to do. 2. Fortunately, there's a way to simplify this process. You can create a shortcut to a path with the use keyword once, and then use the shorter name everywhere else in the scope. Can we use blank abs? Can we, say, use create front of house hosting as host? In listing 7.11, we bring the create front of house hosting module into the scope of the eat at restaurant function, so that we only have to specify hosting add to waitlist to call the add to waitlist function in eat at restaurant. Here we go. We use front of house hosting. We add to waitlist. Here is our module. We then use this namespace, and we can simply use hosting. This is a common thing within languages. I'm glad to see that it's in here. Adding use and a path in the scope is similar to creating a symbolic link in the file system. By adding use create front of house hosting in the create root, hosting is now a valid name in that scope, just as though the hosting module had been defined in the create root. Paths brought into scope with use also check privacy like any other paths. Note that use only creates the shortcut for the particular scope in which the use occurs. Listing 7.12 moves the eat at restaurant function into a new child module named customer, which is then a different scope than the use statement, so the function body won't compile. We have mod, front of house hosting, add to waitlist, we use create front of house, we have a module called customer, a public function, eat at restaurant. This will not work because the use is within the scope of customer, not within the scope of this public function. This use is within the scope of create, and customer is not within the scope of create. The internals of customer is not within the scope of create, but customer is, just to clarify. So we cannot use hosting inside of this function. Make sense? The compiler error shows that the shortcut no longer applies within the customer module. Cargo bill, compiling this thing, unused import here. Error, failed to resolve. Use of undeclared crate or module hosted. And that is here. Here is the use of undeclared crate or module hosting. For more information, right here. Notice that there's also a warning that the use is no longer used in its scope. To fix this problem, move the use within the customer module too, or reference the shortcut the parent module with super : hosting. Oh, that's cool. Within the child customer module. That's really cool. I quite like that. So if we just did super : hosting, we wouldn't have to re-add the use every time we had a function within a different module within our base root. Makes sense. Notice there's also a warning that the use, we've already read that, creating idiomatic use path. In listing 7.11, you might have wondered why we specify use create front of house hosting, and then called hosting add to wait list in eat at restaurant, rather than specifying the use path all the way out to the add to waitlist function to achieve the same result as in listing 7.13. We have simply added this, allowing us to bring in add to waitlist. At which point we can just run add to waitlist. Although both listing 711 and 713 accomplish the same task, listing 711 is the idiomatic way to bring a function into scope with use. Bringing the function's parent module into scope with use means that we have to specify the parent module when calling the function. Specifying the parent module when calling the function makes it clear that the function isn't locally defined, while still minimizing repetition of the full path. The code in listing 713 is unclear as to where add to waitlist is defined. Completely agree? People will still do this, no matter what you try to stop, or how you try and stop them, unless you literally can't do it in a language. Secondarily, with like go-to definitions, stuff like that, this honestly isn't that important anymore. Still though, I'm still going to use it the way that they say is idiomatic. On the other hand, when bringing in structs, enums, and other items with use, it's idiomatic to specify the full path. In listing 714, we show the idiomatic way to bring the standard library's hash map struct into the scope of a binary crate. Okay, so when bringing structs, enums, and other items, we can just get in the actual thing instead of bringing in collections, then using collections, : hash map. Make sense? There's no strong reason behind this idiom. It's just the convention that has emerged, and folks have gotten used to reading and writing Rust code this way. I think that it is quite idiomatic. We have a function which is being called from some module, versus here, where we are utilizing some struct which we are bringing in. I think that's fine. There's no... the exception to this idiom is if we are bringing in two items with the same name into scope, with use statements. Because Rust doesn't allow that. Listing 715 shows how to bring two result types into scope, and of the same name but different parent modules, and how to refer to them. Use standard format, use standard IO. We have format, : result, and IO, : result. Okay, yeah, so if we have two different things with the same name, we have to bring in the parent module, it seems. Bringing two types with the same name into scope requires using their parent modules. That's a good way to differentiate them. As you can see, using the parent modules distinguishes the two result types. If instead we specified use standard format result, use standard IO result, we'd have two result types in the same scope, and Rust wouldn't know which one we meant when we used result. Providing new names as the keyword. There's another solution to the problem of bringing two types, the same name, into scope. Use, : after the path. We can specify as and a new local name, or alias, for the type. Listing 716 shows another way to write the code in listing 715 by renaming one of the two results types as. Yep. So we can just use result as IO result. Makes sense? Renaming a type when it's brought into scope with the as keyword. That's what happened. And the second use statement, we chose the new name IO result for the standard IO result type, which won't conflict with the results from standard format that we've also brought into scope. Listing 715 and listing 716 are considered idiomatic. The choice is up to you. Personally, I do prefer this situation, but I can understand why somebody would want this. In a compiled language, this... Right. So the reason why a lot of people might go for this instead is due to the fact in a lot of non-compiled or garbage-collected languages, if you bring in just format, if you're just to bring format and IO in, you bring in the entire module, everything within it, and it would bring up a lot more memory, a lot more resources. However, here, if we bring in the result, we just bring in one singular thing. Same with this when we are naming it. In JavaScript, this is absolutely the case. Bringing in it like this brings in the entirety of format, the entirety of IO, no matter what you use. However, since this is a compiled language, the non-garbage collected language, I'm pretty certain that this is just going to bring in the things which we use. I don't see why it would bring anything else in. It has the ability not to. Providing new names with the... Oh yeah, we've already read that. Re-exporting names with pub use. When we want to bring a name into scope with the use keyword, the name available in the new scope is private. To enable the code that calls our code to refer to that name as it, to enable the code that calls our code, refer to that name as if it had been defined in the code scope. We can combine pub and use. This technique is called re-exporting, because we're bringing an item into scope, but also making that item available for others to bring into their scope. Okay. I'd like to see an example of where that's used exactly. I can't think of any use in code that I've written previously. Alright, we have file name, source, ip.rs, class, hosting, waitlist, make, yep. So we just have, here it is, public use. That's all we're doing. For this change, external code would have to call the add to waitlist function by using the path restaurant, front of house, hosting, add to waitlist. Now that this pub use has re-exported the hosting module from the root module, external code can now use the path restaurant, hosting, add to waitlist instead. Re-exporting is useful when the internal structure of your code is different from how programmers calling your code could think about the domain. For example, in this restaurant metaphor, the people running the restaurant think about front of house and back of house. But customers visiting the restaurant probably won't think about the two parts of the restaurant in those terms. With pub use, we can write our code with one structure, but expose a different structure. Doing so makes our library well organized for programmers working on the library and programmers calling the library. That's a terrible sentence. That's just a terrible sentence. Who wrote this? Doing so makes our library well organized for programmers working on the library and programmers calling the library. Working with the library or calling the library would have... never mind. Who cares about semantics? We'll look at another example of pub use and how it affects your crates documentation in the Exporting a Convenient Public API with Pub Use section in Chapter 14. We're currently in Chapter 7, so that won't be for a while. Using external packages. In Chapter 2, we programmed a guessing game project. It's an external package called rand to get random numbers. To use rand in our project, we added this line in cargo.toml. Rand equals, sorry for the scrolling, 085. Adding rand as a dependency in cargo.toml tells Cargo to download the rand package and any dependencies from crates.io and make rand available to our projects. Then, to bring rand definitions into scope with our package, we added a use line stating with the name of, Then, to bring rand definitions into scope of our package, we added a use line starting with the name of the crate, rand, and listing the items we wanted to bring in scope. Recall that in the Generating a Random Number section of Chapter 2, we brought the RNG trait into scope and called the rand RNG function. Here's this snippet from, oh my lord, that's not what we want. Thank you. Members of the Rust community have made many packages available at crates.io. And pulling any of them into your package involves these same steps. Listing them in your package's cargo.toml file, and using use to bring items from their crates into scope. Note that the standard std library is also a crate that's external to our package. Because the standard library is shipped with the Rust language, we don't need to change cargo.toml to include standard. But we do need to refer to it with use to bring items from there into our package's scope. For example, with hashmap, we would use this line, standard collection hashmap. This is an absolute path starting with standard, the name of the standard library crate. whereas crate would be the name of our project in and of itself, or specifically in that section of the project. Using nested paths to clean up large use lists. If we're using multiple items defined in the same crate or the same module, listing each item in its own line can take up a lot of vertical space in our files. For example, these two use statements we had in the guessing game in listing 2, 4, and items from standard into scope. We have standard, comp, ordering. We also have standard, IO. Instead, we can use nested paths to bring the same items into scope in one line. We do this by specifying a common part of a path, followed by 2 colons, then curly brackets around the list. Around a list of the parts of the path that differ, as shown in listing 718. Comp, ordering, and IO. I wonder, in this situation, could we have perhaps if we had comp result and IO result, could we then put colon here, result, comp, comma, IO, and then colon result? I'm not going to test that out, but the way this is worded makes it seem like this is the intent. In bigger programs, bringing in many items into scope from the same crate or module using nested paths can reduce the number of separate use statements needed by a lot. We can use a nested path. Yeah, I think that's... I really want to try it out, but we're in a flow. We're near the end of this. Okay. We can use a nested path at any level in a path. What? Yeah, okay. Which is useful when combining 2 use statements that share a subpath. For example, in listing 719, there's 2 use statements, one that brings standard IO into scope and one that brings standard IO right into scope. 2 use statements, or one is a subpath of the other. The common part of these paths is standard IO, and that's the complete first path. To merge these 2 paths into one use statement, we can use self in the nested path, as shown in listing 720. Standard IO, bring in self, and separately write. Why would you want to do that? I really don't see why you'd want to do that. I guess if you're just writing using the write 30, 40, 80 times, IO colon write, you could just... Well, I guess it would allow for the more idiomatic usage of write, if this is an enum or stroke. Alright. This line brings standard IO and standard IO write into the scope, the glob operator. If we want to bring all public items defined in a path into scope, we can specify that path followed by the star glob operator. This use statement brings all public items defined in standard collection into the current scope. Careful with using the glob operator. Glob can make it harder to tell what names are in scope and where a name is used in your program was defined. Yeah. If I see this, I'm going to hate the programmer. I'm going to blame them and then yell at them in Slack. The glob operator is often used when testing to bring everything under test into the tests module. I guess unless we're doing this. We'll talk about that in the how to write test section in chapter 11. The glob operator is also sometimes used as a part of the prelude pattern. See the standard library documentation for more information on that pattern. I am quite curious. Is this long? No. Rust comes with a variety of things in a standard library. However, if you had to manually import every single thing that you used, it would be very verbose, but importing a lot of things that a program never uses isn't a good idea either. Balance needs to be struck. The prelude is the list of things that Rust automatically imports into every Rust program. It's kept small as possible and is focused on things, particular traits, which are used in almost every single Rust program. Yep. Preludes can often multiple types. As such, you'll find the preludes in the standard libraries, such as standard IO prelude. Various other libraries in the ICU system may also define their own preludes. Okay. So prelude is something that, standard IO has prelude, which will bring in a bunch of stuff from standard IO, which is generally used with standard IO, and other libraries can have other preludes, which will have everything we need to work with that library as a basic system. Makes sense. Okay. The glob operator is also sometimes used as part of the... Yep, we've got that. let's go to the quiz. Which of the following statements best describes the function of the use keyword? Use indicates to the compiler that an item will be used and should be optimized. No. Use copies the contents of an item from one module to another. No. Use reduces verbosity, referring to items in the reuse path. I believe that's correct. Use allows access to items that circumvent normal privacy rules. Incorrect. I believe this is the most correct here. It doesn't copy the content of an item from one module to another. It simply reduces verbosity by of referring to items in the use path. Secondarily, consider this module and use statement. We have mod parent, function A, public function A, function B, and then we have public module child. You think the third? Yeah, I completely agree. I think that we may have a bit of a delay. Yeah, we just got... Yeah, I think we're both correct there. What do we have inside main? What is the total number of paths that can refer to A, B, or C? Not including those that use self, super, or create. Write your answer as a digit, such as 0, 1. For example, if the only two valid paths were A and parent B, then the answer would be 2. What? Inside main was the total number of paths that can refer to A, B, or C. A, B, or C. Where's C? Within child. Right. We have use parent, colon, bringing in everything, and child as alias. So C can be gotten through alias, colon, child. 1 is correct. You think that there's only one path? I disagree. We have A, B, or C. A can be brought in. C can be brought in by alias or as itself. We have child, colon, C. We also have alias, colon, C. We have A, which can be brought in as itself. Parent, colon, A. I believe that is everything, though. That's 1, 2... Oh. The other section? Sorry about that. Yeah, this delay is kind of weird for me. I keep missing stuff. Also, your timing is weird. It's 8:01 here, but you're saying 8:02. Sorry about that. Just the delays got us. I may be able to fix that myself. Sorry. But I do believe it's 3. We have alias, colon, child, colon, C. We have... Sorry, alias, colon, C. Then we have child, colon, C. And we have just A, parent, colon, A. That would be 3 different ways where somebody could do it. Self, super, create. So I think that's 3. I think that's 3. I got that wrong. How many ways can you refer to it? We did get this correct. That is 3. You think 1 could be correct for this, though? It doesn't exactly copy it in, I don't think. Maybe it does. I guess it kind of does. There are 5. There are 2 paths to A, parent, A, and A. Okay, yeah. There are no paths to B because it's private, and there are 3 paths to C. Parent, child, C, and alias C. Okay, fine, be like that, I guess. I don't think that really matters, though, to get that wrong, honestly. Though I'm pretty certain other people probably saw that and thought instantly, yep, there's 5. Those people are simply better than me. Separating modules into different files. So far, all the examples in chapter defined multiple modules in one file. When modules get large, you might want to move their definitions to a separate file to make the code easier to navigate. For example, let's start from the code in listing 717 that have multiple restaurant modules. We'll extract modules into files instead of having all. It was the third one is correct. I'm sorry, I don't understand what that means. Sorry about that. Again, the delay is very weird for us. You were right on that, though. You did get the third is correct. So, so sorry about this survey. It must be frustrating. I may just be an idiot, to be clear. And by may, I mean I am. Sadly. Thank you for being here, though. I do appreciate it. For example, let's start from code listing 717 out of multiple restaurant modules and extract the module into file instead of having all the modules defined in the create root file. In this case, the create root file, source lib.rs, is source lib.rs, but this procedure also works with binary creates, whose create root file is source main.rs. First, we'll extract front of house module to its own file. Remove the code inside the curly braces for the front of house module, leaving only the mod front of house declaration. That source lib.rs contains the code shown in listing 721. Note that this won't compile unless we create the source front of house.rs file in listing 722. Alright, so I guess we're going to be doing this. This is a follow along procedure. Is this not the correct place? No. I thought I had this somewhere. Ah, yeah, I guess it's right here. Look, I'm not good at organization, okay? I'll leave that to people who are better than me. Right? So we simply have mod front of house. Hello? Can we? Sure. Why would it work? What exactly are we doing? Sorry for the delay. Let's just rewrite this entirely. We have a mod front of house. We have a pub use. Unresolved module. This is oh yeah, it won't compile until we do the next little bit. Let's just take this out. I know it's probably quite annoying to watch me just do this. You can type this out on your own. Always better to learn this yourself. We have these three things. We have front of house, which is going to be its own little thing. We are going to bring this out into its own file. What is the file called? Here we are. This is correct. Looks like it. Yep, looks like that worked. Unresolved import. Create front of house hosting. No hosting in front of house. Where's hosting? Yes, there is. Well, I guess we'll see a little bit. Okay, so next, place the code that was in the curly brackets into a new file called source front of house.rs shown in listing 722. The compiler knows to look in this file because it came across the module declaration in the create root with the name front of house. Okay, we have front of house.rs. We have, okay, so yeah, we don't have to say that it's a mod, we can just do this. Oops. Does that work? I guess so. Here we go. Works perfectly fine. Really sorry for this. I am quite tired today. I don't think there's been a single one of these where I haven't been extremely tired. Guess that's just Tuesdays for me. Note that you only need to load a file using a mod declaration once in your module tree. Once the compiler knows that the file is part of the project and knows where in the module tree the code resides, because of where you've put the mod statement, other files in your project should refer to the loaded file's code using a path to where it was declared, as covered in as for referring to an item in the module tree section. In other words, mod is not an include operation that you may have seen in other programming languages. Next, we'll extract the hosting module into its own file. The process is a little bit different because hosting is a child module of front of house, not of the root module. We'll place the file for hosting in a new directory that will be named for its ancestor in the module tree. In this case, it'll be front of house. Right? Pretty simple. We have front of house, which will be a directory. And within this directory, we will be adding a file called hosting.rs. Within this file, we will be taking out hosting, and I believe we'll just be pasting it here. File not included in module tree. Unlinked file. Perhaps that's not correct. Right, to start moving hosts, we'll change source front of house.rs to contain only the declaration of the hosting module. Oh, I see, yeah. We forgot declaration. Oh, of course, we just learned that. We don't actually need that normally. We don't need that anyway because of the naming. I don't know why I thought it would be there. But this will work, I believe. Yep. See that table? Use never use, that's fine. File, front of house.rs as public mod hosting. Then we'll create a source, front of house directory, and a file hosting.rs to contain the definitions made in the hosting module, as we just saw me doing there. Inside of front of house hosting.rs, we have a public function add to waitlist. Yep, we also have see that table. If we instead put hosting.rs in the source directory, the compiler would expect hosting.rs code to be in a hosting module, declared in the crate root, and not declared as a child of the front of house module. The compiler's rules for which file to check for which module's code. The compiler rules for which files to check for which module's code means the directories and files more closely match the module tree. What? What? I'm sorry, I've been complaining about wording for a while now. Am I just incredibly tired? I understand what this means, but this was terrible. Did they take English? This is a university. Brown. This is Brown education. This is an American university. The compiler's rules for which files to check for which module's code means the directories and files more closely match the module tree. This is... I'm just going to put in a comment here saying this is terribly worded. Please rephrase. I don't know how to spell rephrase. That's not how you spell rephrase. That's how you spell rephrase. Thank you. You have never been so confused by a sentence? Right, it's not only me. I am incredibly confused. Oh, hello. What is this? What have I done? Oh. Yeah, I guess that yellow is just to say, hey, here's my note. This is so terribly worded. I don't know, man. Okay, let's move on. I'm not going to internally move on. I'm going to be thinking of this for days. But let's start thinking about alternate file paths. So far, we've covered the most idiomatic file paths for the Rust compiler. So far we've covered the most idiomatic file paths the Rust compiler uses, but Rust also supports an older style of file paths for a module named front of house. Declared in the crate root, the compiler will look for the module's code in source front of house.rs, which we covered, source front of house /mod.rs, older style, still supported path. Okay, I've seen this in a few Rust libraries, Rust projects that I've seen. I do prefer this. I think this makes more sense. Everything within front of house should be within front of house, but I guess this is the idiomatic approach, the newer approach that we're trying to get for. So in source, we'll just have like a couple hundred different files with the name of something. And then we'll just have a couple hundred different folders with the rest of that code. For a module named hosting, that is a submodule of front of house, the compiler will look for the module's code in source front of house /hosting.rs, what we covered, and source front of house hosting /mod.rs. Older style, but still supported path. If you use both styles in the same module, you'll get a compiler error. Yes! Just choose one, I like that. Using a mix of both styles for different modules in the same project is allowed, but might be confusing for people navigating your project. Absolutely, pick one. Pick a lane. But you get an error? Oh, only within the same module. Okay. Within the same module, you get an error, but you use it within the same project, you won't. This way, people can just turn over specific modules instead of having to do the entire project in the new system. That's probably why they put it in there. I wonder if they'll ever put in like a strict mode to always error out. The main downside to that style that uses files named mod.rs is that your project can end up with many files named mod.rs, which can get confusing when you have them open in your editor at the same time. That's actually fair. But why won't it allow us to have source /front of house /front of house.rs? Like, I think that would be the best of both worlds. That we can have everything within the same folder, but separately have a file named front of house. The main downside to this style is, we've moved each module's code into a separate file, and the module tree remains the same. The function calls in eat at restaurant will work. Sorry, just got a message. We've moved each module's code out to a separate file, and the module tree remains the same. The function calls in eat at restaurant will work without any modification, even though the definitions live in different files. This technique lets you move modules to new files as they grow in size. Good to see. Note that the pub use create front of house hosting statements in source librs also haven't changed, nor does the use statement have any impact on what files are compiled as part of the crate. The mod keyword declares the modules, and Rust looks in a file with the same name as the module for the code that goes into the module. I'm sorry, who wrote this? I'm going to look them up. The mod keyword declares modules, and Rust looks in a file with the same name as the module for the code that goes into that module. Alright, reading that a second time makes sense, but you could write that so much better. Imagine a Rust package with the following directory structure: foobar, targutoml, source. It's a one-question quiz! Oh dear, I don't know if I can handle this. If I fail this, oh no. So we have live, engine analysis.rs. Contents of each file are this, and this. I'm not reading them. Say that another Rust developer is using the foobar library to create a separate package, and they want to call the run function. What is the path they would write? Alright, so they're using the foobar library to create a separate package, and they want to call the run function. So we have run, where's run? Engine, analysis, and run. Under engine /analysis. So they have foobar, :engine, :analysis, :run. I believe that would be it, right? Right? No. Yes. Right, so we have a module analysis, but we pub use analysis to bring in everything from analysis, which includes run. So we don't actually need analysis. Engine : run will work. I believe so. So we have foobar, which is the name of the package, the library. We're using it in a separate package, and I want to call the run function. We have run, which is in analysis.rs. Engine brings in the module analysis.rs, but it also makes its everything within it public to use from engine.rs. So foobar, engine, run. And they want to call the run function. What is the path they would write? I wonder if it's going to ask us to do this, or if it's going to ask us just to do this, because, well, yeah. It's just the path. We're just looking for the path. Hey, I got that correct. Fantastic. The module tree generated by this directory structure is as follows: foobar, engine, run. Therefore, the path to run is foobar, engine, run. Wow. Thank the Lord. I would have just quit out right now. You would have seen something hit that camera right there, and I would never be on again. My computer would be gone. I'd go live in the woods. I'm very happy about that. Rust lets you split a package into multiple crates and a crate into modules, so you can refer to items defined in one module from another module. You can do this by specifying absolute or relative paths. These paths can be brought into scope with a use statement, so you can use a shorter path for multiple uses of the item in that scope. Module code is private by default, but you can make definitions public by adding the pub keyword. In the next chapter, we'll look at some collection data structures in the standard library that you can use in your neatly organized code. Alright. Sorry, there's a ladybug in here. I never thought that ladybugs were like a pest. There's like hundreds of them in this house. Honestly, I like it though. It's kind of cute. Right, so next is common collections. Rust's standard library includes a number of very useful data structure called collections. Most other data types represent one specific value, but collections contain multiple values. Unlike the built-in array and tuple types, the data these collections point to is stored on the heap, which means the amount of data does not need to be known at compile time. It can grow or shrink as the program runs. Each kind of collection has different capabilities and costs, and choosing an appropriate one for your current situation is a skill you'll develop over time. In this chapter, we'll discuss 3 collections that are used very often in Rust programs. We had this question earlier. You were asking, why would you use a vector over an array? You used to find ladybugs everywhere in your house as a kid and thought it was a conspiracy or something? They're out for me, honestly. I think they're watching me sleep. I think if enough of them crawled into my mouth, I would die. Why have you done this to me? Now I understand the truth of these ladybugs. It is a massive conspiracy. They're going to kill me. Look, if I die, it wasn't suicide. The ladybugs got me. Thank you for that. A vector allows you to store a variable number of values next to each other. A string is a collection of characters. We've mentioned the string type previously, but in this chapter we'll talk about it in depth. A hash map allows you to associate a value with a particular key. This particular implementation of the more general data structure called a map. It is a particular implementation of the more general data structure called a map. Yep, hash maps. Learn about the other kinds of collections provided by the standard library. See documentation. Always use vector. Don't look into hash maps. They're a lie. They're never useful. Every time I've looked into if one was actually useful, it hasn't been. That's a bit of a lie, actually, but still. Creator of C++ agrees with me. Vectors are superior. Showing lists of values within vectors. The first collection type we'll look at is vec_t, also known as a vector. Vectors allow you to store more Are we in a full-on new chapter? I guess we are, yeah, we're in Chapter 8, Common Collections. Is vect, also known as vectors. Vectors allow you to store more than one value in a single data structure that puts all the values next to each other in memory. Vectors can only store values of the same type. They are useful when you have a list of items, such as the lines of text in a file or the prices of items in a shopping cart. Creating a new vector. To create a new empty vector, we call the vec_new function as shown in listing 8.1. Let v vec I32 equal vec_new. Note that we added a type annotation here because we aren't inserting any value into this vector. Rust doesn't know what kind of elements we intend to store. This is an important point. Vectors are implemented using generic. We'll cover how to use generics in your own type in Chapter 10. For now, know that the vec type provided by the standard library can hold any type. When we create a vector that holds a specific type, we can specify the types within angle brackets. In listing 8.1, we've told Rust that the vect in v will hold elements of the I32 type. More often, you'll create a vec with the initial values, and Rust will infer the types of values you want to store. So you rarely need to do this type annotation. Rust conveniently provides the vec macro, which will create a new vector that holds the values you give it. Listing 8.2 creates a new vec I32 that holds the values 1, 2, and 3. The integer type is I32 because that's the default integer type, as we discussed in data types section, Chapter 3. Let vec equal 1, 2, 3. Because we've gotten initial I32 values, Rust can infer that the type of vec v is vec I32, and the type annotation isn't necessary. Next, we'll look into how to modify a vector. Updating a vector. Push, create a vector, and add elements to it. You can use the push method, as shown in listing 8.3. Didn't we already learn this? I feel like this is, I don't know, deja vu. As with any variable, we want to be able to change its value. If we want to change its value, we need to make it mutable using the mute keyword. As discussed in Chapter 3, the numbers we placed inside are all of type I32, and Rust infers this from its data. So we don't need vec I32 annotation. Reading elements of vectors. There are two ways to reference a value stored in a vector, by indexing or using the get method. In the following examples, we've annotated the types of values that are returned from these functions for extra clarity. Listing 8.4 shows both methods of accessing a value in a vector with indexing syntax and get method. We have vector 1, 2, 3, 4, 5. We have third, which is a reference to an I32, making a reference to the third element in the vector. Third element is third. Third option brings in an I32. v.get2. Okay, so that gets an option. Okay, match third. Third. Sum third. Okay, so yeah, I'm guessing that get will allow you to get an index that's not in there. So if we put in like 73 into here, we would get a none. So we can get the section of vector if it exists. Okay. Note a few details here. We use the vector, the index value of 2, to get the third element because vectors are indexed by number, starting at 0. Using ampersand and brackets gives us a reference to the element at the index value. When we use the get method in the index path as an argument, we get an option with a t that takes in a random type that we can use with match. Yeah, I think this is really cool. I quite like that. It also forces us to actually check it instead of being null. At first I didn't really like it, but I really do like the option now, because I can see its use in this specific manner. The reason Rust provides these two methods to reference an element is so that you can choose how the program behaves when you try to use an index value outside the range of an existing element. As an example, let's see what happens when we have a vector of 5 elements and we try and access an element at index 100. Exactly what I was saying with each technique, as shown in listing 5, 8-5. So here we will crash. It will not crash, it will fail to compile. Will it fail to compile, or will it just break at runtime? When we run this code, the first bracket method will cause the program to panic because it references any non-existent element. This method is best used when you want your program to crash if there's an attempt to access an element past the end of its vector. When the get method is passed an index that is outside the vector, it returns none, without panic. Quite useful. You'd use this method if accessing an element beyond the range of the vector may happen occasionally under normal circumstances. Your code will then have logic to handle having either some element or none, as discussed in Chapter 6. For example, the index could be coming from a person entering a number. They accidentally enter a number that's too large, and the program gets a none value. You could tell the user how many items are in the current vector. Give them another chance to enter a valid value. That would be more user-friendly than crashing the program due to a typo. Honestly, I disagree. If you get it wrong the first time, you should be shot. Look, we don't take losers at this company. When the program has a valid reference, the borrow checker enforces the ownership and borrowing rules, covered in Chapter 4. To ensure this reference and any other references to the contents of the vector remain valid. Recall the rule that states you can't have mutable and immutable references in the same scope. That rule applies in listing 8.6. Where we hold an immutable reference to the first element in its vector, try and add an element to the end. This program won't work if we also try to refer to that element later in the function. We have immutable vector 1, 2, 3, 4, 5, let first equal a reference to 0. Then we try and push 6, which would destroy this vector, build a new vector, and this would be a use after free. Attempting to add an element to a vector while holding a reference to an item. Compiling this code will result in this error. Mutable borrow. Here's the error. Do not borrow v as mutable, because it is also borrowed as immutable. We have the immutable borrow, where we have let first equal a reference to the 0th element. We have push, mutable borrow occurs here. And here's the use, where we try and use the immutable. Where we immutably borrow later. Print it out. Trying to print out first. The code, so the reason this fails is, again, due to the fact that this originally is a reference to the 0th element. Before this is destroyed, that a new thing in. Meaning this now points to random memory that any other program could be using. The code in listing 6.8 might look like it should work. Why should a reference to the first element care about changes to the end of a vector? This error is due to the way vectors work, because vectors put the values next to each other in memory. Adding a new element onto the end of the vector might require allocating new memory and copying the old elements in the new space. There isn't enough room to put all the elements next to each other where the vector is currently stored. In that case, the reference to the first element would be pointing to deallocated memory. The borrowing rules prevent programs from ending up in that situation. And here you can really see why somebody might not know that they are doing a use after free. Because they think that just adding something onto this isn't going to destroy V and move it somewhere else. It isn't going to destroy what this referenced originally, because this is just a pointer to where this data is originally stored. If this data is no longer in that location, if you moved house, you're just going up to some random guy's house. That's a terrible explanation. Sorry for that. For more on the implementation details of VecT, type the Rustonomicon. I love the guys who built this. The Rustinomicon. That is terrible. I love it. Iterating over the values in a vector. To access each element in a vector in turn, we would iterate through all the elements rather than using indices to access one at a time. Lesson 8.7 shows how to use a for loop to get immutable reference to each element in a vector of i32 values and print them. Thank you for the bit. Let v equal vec 132.57. For nref in reference v, nref is a type of i32. Let n plus 1 i32 equal dereference nref plus 1. Print out n plus 1. 101, 32, 3, 58. Accessing each element in a vector by iterating over the elements using a for loop. Read the number that nref refers to. We have to use the dereference operator to get the value in nref, because we can add before we can add 1 to it. As covered in dereferencing a pointer accesses its data. We can also iterate over mutable references to each element in a mutable vector in order to make changes to all the elements. The for loop in listing 8.8 will add 50 to each element. Right, we have nref in mutable v, which is a mutable reference to mut v. Yep. Sorry. You change the right. Yep. So we're just creating a mutable v, creating nref, which is this for loop. We're adding 50 to nref, which is dereferenced here, to get the value plus 50. I'm fairly certain we've done all this before, right? Like we've done all this before in previous listings. I don't understand. Change the value that the mutable reference refers to. We again use the star to dereference operator to get to the value in nref before we can use the plus equals operator. Quiz. Which call to this find until function will cause a runtime panic? Alright, so we have find until, brings in a p, so a reference to a vector i32, n, which is an i32, and till, which is a usize. Returning an option, usize. For I in 0, until till, so this is a range from 0 until the till. If b, I, is equal to n, return sum I. Okay, so if the index is equal to n, the thing which we are attempting to find returns sum I. If we get to the end, we return none. What will cause a runtime panic? Right, this goes over. Right, so the issue here is that this goes over. This is trying to get an index that doesn't exist. If we have 1, 2, and 3, and we try and get... Oh, no, never mind. I don't think this will. I'm sorry. We try and get 4. We have from 1 until 4. We try 1 for I, which is 1. It'll hit here. It'll ask for the second element, which is 2. Sorry, no, it is looking for 1, and it'll go 4 times to get 1. Sorry for that. That's a bit wrong on my end. Here we have 3. We are looking for 3, and we'll go 3 sections. Here we are looking for 4, and are going 4 sections. That will be the falter, the failure here, because it'll get to 4, where I is 4. It'll try and access V, 4, the 4th element. No, here's where it will fail. First. Won't it? No, here. Sorry. It'll look for 4, here, and it'll error out, because we don't use the get section of V. Apologies, that was very poorly worded and a bit scatterbrained, but the issue is here. Anything else will work. Yeah, it's the 4th one. Thank you, Sorbet. I think that's fully correct. Determine whether the program will pass the compiler. If it passes, write the expected output of the program if it were executed. We have immutable v, which is a vec new. We have s, which is a string hello. We have v.push s. We have push s with it. Yep. That just destroys v. Adds in hello. Changes the reference here. We have v0, the first place, and we push the string world. So we have s, which is not mutable. S is not mutable. Is that really the issue? That's boring if that's the issue. We're not talking about the vector at all. So we have... Does that push the value, or does that push the reference? I'm pretty sure that fails that. I'm pretty sure that fails. Right? That fails here because this is not mutable. You don't think that's the issue? Alright, well, let's assume that isn't the issue. Fair. We have v0 push world. We have print line where we print out s. Not a reference to s. S itself. The original. And we have new. Which will push hello world. Will it push hello world? Okay, so if this is not the issue, this will compile. The issue is not that this is immutable. And then this is probably copying the value into 0. So if we try and print out 0, that'll be fine. I think this will compile, right? I don't see any issue, right? Yeah, I think it's fine. Unless the issue is that this is immutable. But S doesn't have the copy trait. Well, it's not a reference to S, I guess. So, yeah, if it doesn't compile, if it does say that it doesn't compile, my guess is going to be that we are borrowing S, which I don't think we are. So I think that's fine. Determine whether this program runs and output its output. Let v equal vector string from hello. We have vector with a zeroth element called hello. We have letting a mutable s equal v0, which is an immutable borrow. We have s.push string hello world. I don't think we can because that is not mutable, right? This is not mutable. We can't change v. Can't mutably borrow an immutable. We can't do that. I may not understand what it's asking. This is a solid show of my own stupidity. Yeah, I don't think this will compile. This isn't a reference, so this would be attempting to copy the string, right? If the first one does compile, this one would compile. I don't see why it wouldn't. I really don't see why it wouldn't. Yeah, I don't see why this wouldn't compile. If the first one compiles, this one will compile. Yeah, I think the first one may have failed because of the mutability problem. I'm just going to say this does. We answered one question correct. Right, yep, that was correct. This program does not... What? Right, I don't think this will compile. Okay, this does not compile, and neither does this, for the same reason. So again, my belief is that this will not compile because S does not have the copy trait, so hello will not be able to be copied. What messed us up there, what I believe really messed me and you up, is due to the fact that this has nothing to do with vectors. Let's see the correct answers. This does not compile. Non-copyable types cannot be moved out of a vector by indexing. Only methods such as vec::remove permit moving out of a vector. See, copying versus moving out of a collection. A deeper explanation of why. Okay, so yeah. Right. This is why we messed up, because we were thinking in terms of 8-1. When this was not asking about 8-1, this was asking about 4.3, which makes sense. Like, I knew this was the issue, right? That it does not implement the copy trait and thus will fail. What is the last one? The last one is incorrect for the same reason, right? Oh, the second one might be wrong for the wrong reason. Back push moves its argument, so S is not usable after calling v.push. Therefore, calling println original S is not ownership safe. Oh, okay. So the second one is actually wrong for a different reason. Back push moves its argument. So back push S moves S, meaning S is no longer owned. We cannot use S. That's the issue? That's the issue. I see. So, due to the fact that this does not implement the copy trait, S is moved. From S, S no longer owns S, or hello, this string, and thus cannot be used until V is destroyed. So, pushing here fails us. Using this, I don't think would work either. I think that would falter. I think that would break, because it's not mutable. Okay, I think that these two things make sense. We were just thinking in terms of this chapter instead of in terms of the entire book. Good lesson to move forward. Try and remember the lessons from previous sections. I'll admit I'm not strong on moving and copying. Well, on copying, obviously I am, but moving, I'm not entirely certain I understand fully. Safely using iterators. We'll discuss more about how iterators work in Chapter 13 too. Processing a series of items with iterators. For now, one important detail is that iterators contain a pointer to data within the vector. We can see how iterators work by desugaring a for loop into the corresponding method calls of vec iter and iter next. Okay. This is going to be a thing to grasp our brains around. Alright. So we have, make this larger. At location 1, we have mutable v, which is vector I32, which is equal to a vector 1:2, comma 2. You're getting scared of encountering ownership's issue in the Cliff project? Oh, we definitely will. Don't be scared, though. Be excited. That's good. I don't understand ownership issues personally. I am very excited to get hit with ownership issue, so that I can understand what ownership really is. And be very glad about that, because if there is an ownership issue, Rust is protecting you. That's Rust saying, hey, step back for a moment. This will be an issue. This will be a problem. Instead of something like C, C++, or other languages, which will just say, yeah, sure, that's fine. And then you're crashing people's computers or systems or doing some dangerous stuff to your own PC. Or just making massive security errors. I think it's exciting. I think it's good. Right, so secondarily we have a mutable iter of type iter. We're not using its first type. I32. I don't know what this is. I don't know what that is. v.iter. At location 1, we have v and iter, which both point to a heap piece of memory here with 1 and 2. Of course, this is a hell of a lot more complicated, as iter actually points to a pointer of an iter object, but like it. For now, we can just know that in the end, they both point to the same data. N1 at location 2, N1 which is a reference to an I32, is equal to iter.next.unwrap. So N1 is equal to 1. Yes, okay. Okay, I think I see. So V is simply a pointer to 1. Okay. V is the vector, which is a pointer to the entire section of heap memory. Iter is a pointer to the first piece of memory 1. At location 2, we have iter.next, which will pass back. We haven't done this before, I don't think. It'll pass back a pointer to the first value, which N1 is now pointing to, and then changes point from one section to the next from the vector. So iter.next, pass back 1, the first section of the vector, and then 2, iterate on itself. Then we unwrap, saying, hey, this is probably a, what is it called? An option. It says sum of type I32 and none to be able to ensure that we actually have a part of the iterator. Okay, and then it just passes back the 1 reference here. At location 3, we have N2 equals reference I32, iter.next.unwrap, same thing. N2 will point to 2. Iter will die. It'll no longer be useful because it iterates out the vector. I wonder if this actually is in the backend pointing to some random memory behind 2 here. But hey. Lastly, we have let end option reference I32 equal iter.next. What does that mean? End is none. Okay, so end is just the none option. Makes sense? Or the none enumerable, which is an option. Yeah, the none option makes sense. That is what it is. Okay, makes sense. Observe that the iterator iter is a pointer that moves through each element of the vector. The next method advances the iterator and returns an optional reference to the previous element. That's a much better description than I put forward, and also very well written. Maybe they could get this guy to rewrite some of the previous stuff. Either some, which we unwrap, or none at the end of the vector. This detail is relevant to safety using vectors. For example, say we wanted to duplicate a vector in place, such as 1, 2, becoming 1, 2, 1, 2. A naive implementation might look like this, annotated with the permissions inferred by the compiler. We have function, dupe in place, bringing in a mutable reference to an I32, a vector of I32s. We have for and rep in v.iter, reference v, loses write. v.push, the reference to nref. Yeah, we have to make this mutable. We have to borrow and make it mutable to create a mutable borrow. Notice that v.iter removes the write permission from the dereferencing of v. Therefore, the v.push operation is missing the expected write permission. The Rust compiler will reject this program with the corresponding error message. Cannot borrow dereference v as mutable because it is also borrowed as immutable. Immutable borrow occurs here. Right, we're borrowing right here. Create nref, which will be each element. Immutable borrow later used here. v.push nref. Oh no, I guess that wasn't the actual issue here. The actual issue was that this is borrowing v.iter. You can't alter v while nref exists. we'd have to be 4 in a range for each element in nref. Yeah, that makes sense. So because nref is a pointer to the first element of v, we cannot change v because it will be destroyed when we try and push it. Meaning nref will point to just random data. And that is a bad thing. We can't just add in random data to our program. That's a use after free error. That's bad. As we discussed in Chapter 4, the safety issue beneath this error is reading deallocated memory. As soon as v.push1 happens, the vector will reallocate its contents and invalidate the iterator's pointer. So to use iterator safely, Rust does not allow you to add or remove elements from the vector during iteration. That makes sense. One way to iterate over a vector without using a pointer is with a range, as I thought, like we used for string slices in Chapter 4.4. This is we're just going over previously done content. For example, the range 0 to v.length is an iterator over all indices of a vector v, as seen here. Mutable vec v, vec I32, vec 1, 2. Let mutable iterator range usize, range of type usize, equals 0 until the length of v. Let il usize iter next unwrap. At nl equal v1. At location 1, we have v, which is pointer to the heap memory, and we have iter, which has inside of our stack memory the start 0 and the end 2. We have at location 2, at the end of this file, we have v, which is a pointer to 1 and 2, the entire heap memory. We have iterator 1, which is 0. Iterator 1 is just the iter. This range, 0, 2. Dot next, dot unwrap. So this will bring in 0 as I1. And 1 will equal, we have reference v, I1. We get the value here, out to n1 for 0. So the first element, 1, will output. And in the end, we have iter, which has iterated the start point. Make sense? That is a reasonable way to do this. So instead of taking in the value, bringing it to nref, and then altering v at a later point, we have simply created an iterator which will increase in size every time we hit next until it hits the end point, and use that to get the value out of v. Right? Using an enum to store multiple types. Vectors can only store values that are the same type. This can be inconvenient. There are definitely use cases for needing to store a list of items in different types. Fortunately, the variants of an enum are defined under the same enum type. So when we need one type to represent elements of different types, we can use define and use an enum. For example, say we want to get values from a row in a spreadsheet, in which some of those columns in the row in which some of the columns in the row contain integers, some floating point numbers, and some strings. We can find an enum whose variants will hold the different value types. All the enum variants will be considered the same type, that of the enum. Then we can create a vector that holds that enum, and so on. Ultimately holds different types. We've demonstrated this in listing 8.9. We have spreadsheet cell, which can hold an integer, float, or text. We have a vector called row, which holds separately 3 different elements. One is an integer, one is some text, and one is a floating point number. That makes sense, since this enum is in and of itself a type, which can hold the value of these 3 things. We can, if set correctly, a vector of type spreadsheet cell, which can hold any of these three values. Rust needs to know what types will be in the vector at compile time, so it knows exactly how much memory on the heap will be needed to store each element. We must also be explicit about what types are allowed in this vector. Rust allowed a vector to hold any type, there would be a chance that one or more of the types would cause errors with the operations performed on the elements of the vector. Using an enum plus a match expression means Rust will ensure, at compile time, that every possible case is handled, as discussed in Chapter 6. If you don't know the exhausted set of types a program will get at runtime to store a vector, the enum technique won't work. Instead, you can use a trait object, which we'll cover much later. Now that we've discussed some of the most common ways to use vectors, be sure to review the API documentation for all the many methods used defined on Vec by the standard library. For example, in addition to push, a pop method removes and returns the last element. Glad that exists. I like pop. Dropping a vector drops its element. Like any other struct, a vector is free when it goes out of scope, as annotated in listing 8-10. Let v equal vec 1, 2, 3, and 4. When a vector gets dropped, all its contents are also dropped, meaning the integers it holds will be cleaned up. The borrow checker ensures that any references to contents of a vector are only used while the vector itself is valid. Let's move on to the next collection type, string. Question 1. Determine whether the program will pass the compiler. To pass this, write the expected output of the program as if it were executed. We have a mutable v, which is vector 1, 2, 3, or I in... Nope, that won't work. Just went over this. I is an immutable reference to v. If we push I, v from here, gets destroyed, and we get a new vector referencing v. I is no longer able to be used. Thus, we falter. This does not compile. Same thing here. We have a mutable v, which is vector I32, bringing in a vector 1, 2, 3. Vector 2, mutable I32s, is a new vector. Or I in mutable v. We don't need that. That's not needed. We have v2.push I. I think that's fine. So v2 will now equal 1, 2, 3. This is just copying over. At which point, when I is done, I will be destroyed, no longer usable, and thus ownership is moved back to v. I think that's fine. Dereferencing v2 0 equals 5. I believe that's fine. I think that's fine. We now have 5, 2, 3. Let a equal reference, dereferencing 0. So that's 5. A will equal 5, and b will equal v0, 1. That's 5 space 1. I see no issue with that. I think this will actually just output 5 space 1. We're not utilizing v within here. We're not trying to mutate it at all, even though we said we are. We're not. I is destroyed, so we can use v2 at a different point. Can we use v2? Sorry, so we can use v at a different point. We can use v2 even though we've pushed it, because it's still living. I see no issue here. Yeah. I agree with you, Sorbet. Let's submit. Got that wrong. Really? This does compile. What? What? Really? Is it because it's not dereferenced? By 5. Oh, I see. I see. Okay. This is something I'll always mistake. We are not. I is not actually 1, 2, 3. I is a reference to 1, 2, 3. That's what that means. I looked at it and thought, wow, that's dumb. I know what I'm talking about. This is hilarious. Yeah, yeah. Okay. That's entirely fair. That makes sense though. I feel like a bit of a fool. I has the type reference mutable I32, meaning it is a pointer to a number within V. So if we push I into V2, then V2 contains a pointer to V. Therefore, mutating V2 0 actually mutates V0. Yeah, I see. Alright, we only have a bit of time left, and this is a fairly long section. Getting into it before the time ends, I think, would be a failure. We get through like here, what is a string, and then next time we'd have to go into creating a string without knowing what a string is. Alright. Thank you again for joining me, Sorbet. Always glad to have you. Same the others can come in, but fair enough. Enjoy your week. I'll see you on Sunday, I believe. But I think that is it for today. I am going to have to end now. Right? Goodbye.